Hello and welcome to Cambridge Skeptics Live. Cambridge Skeptics are a not-for-profit community organisation for the promotion of positive skepticism and critical thinking skills in the Cambridge area and beyond. Tonight we are joined by Dr Steve Barrett, who's going to be talking to us about some of the misconceptions people have about the universe. Our programme for this evening is a little bit different to we normally do. Steve has brought 4 different topics we're going to cover, and we're going to go through them in turn. He's going to introduce them for a bit, and then we're going to have a little bit of a discussion about each one. So without any further ado, I will hand over to Steve to introduce himself and the first topic. Steve.
Thank you. So yes, this is going to be a little bit of a jump around between different topics that over the years I've picked up as being the source of misconceptions from a lot of different people. I've given talks in astronomy, and I've picked up lots of little bits and pieces. And I'm going to be talking about misconceptions in the approximate areas of an expanding universe, looking at the nature of matter, looking at rocket science, it can't be that difficult surely, and in quantum mechanics. And along the way, I'm going to be splashing on the screen a few slides that I've extracted from other talks that I've given in the past few years. But before starting, let's just remind ourselves that there is no reason why the universe should be understood by us. So I love this quote from Einstein: the most incomprehensible thing about the world, or the universe if you prefer, is the fact that it is comprehensible. So misconceptions and confusion is perhaps not that surprising. So let's get stuck in for the first topic, which is an expanding universe. So we think the universe started with a Big Bang, but a question that I'm always getting is, well, where was that? In other words, where should I point my telescope to see the Big Bang? Surely it's out there somewhere. And that's a misconception based on the idea that you can step out of the universe and look back at it. And this was rife when the James Webb Space Telescope was launched, because lots of people were saying the James Webb can look back in time. And so the question was raised, can the James Webb see the Big Bang? Or indeed, if it looks at the Earth, if it's looking back in time, will it see dinosaurs, for instance? To get some idea of what's going on, we have to think about how the universe expands. In other words, how its size changes with time. So we are here at the now point with a relative size of 1, and you can see that in the past the universe was smaller. Notice that we don't know exactly when the Big Bang was, because it depends on which of those coloured curves we're actually on. And the coloured curves are different because the content of the universe determines how it's going to expand. For instance, if the universe was full of a lot of matter, then the universe would end in a big crunch. We would follow the orange curve, and in a few billions of years into the future, the universe, after expanding a little bit, will start to contract because gravity will pull everything back. A so-called closed universe. But we don't think that's the universe we're in. We think we're in a universe in which the amount of matter and the amount of energy is such that we're sitting on the red curve. In other words, the universe will continue to expand indefinitely into the future and simply get larger and larger. Space will continue to expand essentially forever, a so-called flat universe. But I figured that this was an interesting challenge, which is why I thought, well, how far can you look back in time? What is the most distant object you can ever hope to capture with a camera? I decided to try that without a telescope. I put a camera on a star tracker and pointed it at a bunch of stars in the sky where I was hoping to catch a quasar. A quasar is a galaxy with a very bright nucleus, and that little dot at the center there is a quasar on the other side of the observable universe. Most of the light from this object is in just a pixel or so of the picture I took with my digital SLR camera. What's intriguing about this object is the distance and the look back time. Now, the only way we can quantify these things, the only thing we can actually measure about a very remote object is its redshift, how much its light has had its wavelength stretched. And if we think about a very distant object moving away from us and ask, well, how far away is it? And think about the light traveling from the object to us, it's very difficult to say how far has the light actually traveled, because as the light is traveling, space is continuing to expand. It's like a swimmer swimming through water where the water is receding because of the tide. Or if you like, an ant moving along a rubber band, and then somebody is stretching the rubber band. Trying to work out how far the light has traveled is rather tricky. But we can use this idea of if the light has been stretched, and we can measure the stretch by using spectroscopy, we can actually start to convert the stretching of the light, the so-called redshift, into a distance. And we can work out how far the object was, the blue line, how far the light has traveled, the green line, and how far away the object is now, the red line. And we can do that for any given redshift. Now, this particular object that I photographed with my camera happens to have a redshift that's there, and we can read off those numbers. And so we find that this particular object that I photographed was some 5 billion light years away when the light was emitted, and the light has been traveling for some 12.4 billion years. That's 90% of the lifetime of the universe. It's incredible that you can capture an image like this without using a telescope. And because as the light was traveling, the universe continued to expand, so the object got further away and is now about 25 billion light years away. And one of the biggest misconceptions about the expanding universe is just how fast it's expanding. If you look at the blue and the red, it's receded from us from 5 to 25 billion light years, and it's done this over a time period of about 12 billion years. It's traveled 20 billion light years in 12 billion years. That means it's receding from us faster than the speed of light. Despite the fact that this object, this quasar, is receding from us faster than the speed of light, it is still possible to capture that light and record it in a camera. And this whole idea of how can space expand that fast, and if it is expanding that fast, how on earth can we see the light from these distant objects? That is one of the big misconceptions about an expanding universe. We might think that if we were to plot on a distance and time graph the light coming from the quasar to us, we tend to think, common sense tells us, the light will go from the quasar to us according to that dotted line. But no, because the universe is expanding faster than the speed of light, the light actually gets dragged backwards. For billions of years after the light left this quasar, it was getting further away from us. The light is trying to come in our direction, but the expansion of the universe, like a swimmer moving through water that's moving faster than the swimmer can swim, the light gets dragged backwards. And only after a few billion years does the light finally reach us, over a time period, in this case, of some 12 billion years. I think it's absolutely incredible that A, this happens, B, we can sort of make sense of it, and C, it is actually possible to record this light with a camera without using a telescope. So I think this is a good point just to stop and see what we can do in terms of discussion of these various points.
Okay, so to touch on the bit you just covered, the light is moving away from us. How, if the universe is expanding and it's expanding at an accelerating rate, or at least at a consistent rate, at least it's not expanding at a slowing rate, how does it
ever reach us?
Yes.
Yes, and that is the second most common question. Is after, how on earth can space expand that fast? And the first thing to say is space can expand at any speed it wants to. It's not limited by the idea of a speed of light speed limit. That is only for objects moving through space. So space itself can expand as fast as it wants to, and indeed was expanding very rapidly in the early universe, and is now slowing down a little bit. The idea of an accelerating universe, that's easier to put to one side for the moment, because the acceleration doesn't make a huge difference to the argument of how light can reach us. And if anybody's interested, I can post at a later date, perhaps, or to you guys later, a little sort of analogy that I put together to try and explain how it is that light can reach us. But the bottom line is, light is trying to move through space, even though space is expanding very rapidly. And yes, it gets dragged backwards, but it makes a little bit of headway. And by making a little bit of headway, it's now in a region of space which is expanding not quite as fast. but it's still going backwards. But it makes a little bit of headway, and it's now in a region of space which is expanding not as fast. Still going backwards, but every second that goes on, every year, it makes a little bit of headway, and it ends up in space which is not expanding as fast. It's like a swimmer who's getting pulled away from the shore by a receding tide, but is making a little bit of headway and is now in slightly slower moving water. So eventually they do claw their way towards the beach, or in the case of light, it eventually can overtake that and end up, that curve ends up coming back and the light ends up reaching us. But it is one of these many things that is absolutely not intuitive, because common sense does not prepare you for how on earth can that work, because it's not something you can ever see in the world around you. And that's the problem with most of these misconceptions.
So I guess, go ahead, Chris.
Are you saying our part of the universe isn't expanding as quickly as other parts of the universe? Is that because of Brexit?
What I'm saying is, when you think about space expanding, the Hubble constant, let's ignore the fact that the Hubble parameter is actually changing. If you think of the Hubble constant, that says how fast are galaxies moving away from us divided by their distance. That is a ratio that is essentially fixed at the moment. It's 70 kilometers per second per megaparsec. So in other words, galaxies a long way from us are receding from us much faster than galaxies that are much closer to us. So it's nothing to do with where we are, it's simply our perspective. In terms of how fast are these objects moving relative to us, the closer objects are not receding as fast as more distant objects. So as long as the light can make some headway and get a little bit closer to us, it finds itself in space which is not expanding relative to us quite as fast.
So the analogy I've heard, and correct me if I'm wrong on this, is imagining having like a piece of elastic with knots tied at regular intervals, and if you stretch the elastic, the one furthest away from the knot on the left, no, the one furthest on the right, will move away faster than the knot immediately next to it.
Yep.
Even though
the idea of a rubber band is a good analogy in that sense. So if you think of the ant moving on the rubber band, then the rubber band might be stretching such that the ant is going backwards, but it's still making a little bit of headway, even though on the whole it's going backwards. As long as it keeps making a little bit of headway, it will eventually walk its way to the point where it's walking forward, not backward. But so it's the sort of thing that hand waving is one thing, but a good analogy or a good diagram helps.
Yes, yeah. So to return to the question which you yourself raised at the beginning, and that you said it was a common one, why can't we use the James Webb Telescope to see the Big Bang? And where is it? Where would we need to point it if we were looking for it?
Okay, the straightforward answer to where was the Big Bang is the Big Bang was everywhere, because the Big Bang was the creation of the universe. And the misconception is to think that you can step out of the universe and look back and see this little explosion. People think of the Big Bang, because that's how it's portrayed, as an explosion in space. If you're standing in space and looking at a point, you see something go bang. That's not really what the Big Bang was all about. If the Big Bang was the creation of the universe, then everything was made at that point, and everything that we know is inside what was originally a very small sphere expanding into the observable universe that we see today. What you cannot do is step outside of that and say, oh, look, there it is, I can see the Big Bang. So in that sense, the Big Bang is all around us, because we can see, for instance, the afterglow of the Big Bang. That's what the cosmic microwave background is. And we see that in all directions. No matter which way we look, we see this afterglow of the Big Bang, because everything that we see is inside the observable universe, and all of that was originally in a very small volume, but you can't imagine stepping out of the universe and looking back at it to see the Big Bang. So the misconception there is the idea of what we mean by the universe, and can you step outside of it in order to see the Big Bang occur? So the other point was, how do you see the Big Bang? Well, you can't see back to the Big Bang. The best you can hope for is to see the cosmic microwave background. That was the first time at which, as the universe expanded, the first point at which the universe became transparent and allowed light to travel through the universe. That's the point at which the light was released, and that's what we see as the microwave background. We cannot ever see any further back in time than that. So the James Webb Space Telescope will be able to see further back in time than the Hubble Space Telescope, but it will never see back to time zero.
That's fair.
Cool. Okay.
So
Sam, did you have another question, or should we move on?
I have two other questions.
Go for it, and then we'll move on to the next topic.
So, why am I not getting bigger if everything's expanding?
Did I say everything's expanding? The universe is expanding.
Okay.
Galaxies.
Okay, so why am I not getting bigger if the universe is expanding?
Yeah. So as we get older, our waistlines might expand, but on the whole, the universe is expanding if you look at it on a large enough scale. If you look at it on a small scale, meaning essentially a galaxy or a star or a planet or us, we are held together by forces which don't give a damn about the fact that the universe is trying to expand. In other words, we are made of atoms, and atoms are dictated by the laws that say this charged particle is attracted to this charged particle, and that's got nothing to do with gravity and nothing to do with the fact that the universe is expanding. So on a small enough scale, the size of a structure is determined by forces that don't care about the fact that the universe is expanding. Whereas galaxies billions of light years away are simply essentially static, but are being carried along by the fact that space is expanding. I guess that's another misconception, thinking of galaxies flying through space. Strictly, they're not. The galaxies are being carried along by the expanding space. And smaller structures are dictated by other forces.
Yeah, so it's the space between the galaxies that's expanding rather than the galaxies. Yeah. Yes.
You look at a video like the one I showed, and it gives the impression that things are flying through space. But that's because that's what common sense tells us. Common sense doesn't allow for the idea that everything is stuck in space and space is expanding, because that is not a concept that we are usually comfortable with. It's not a concept that we're raised with as children. It's something that we have to learn as adults, that space is expanding, and then you get into the arguments of, well, how can space expand if there's nothing there? And then you get into other arguments.
How do we know that our measurements to these stars are reliable?
Do you mean stars or do you mean galaxies?
Either.
Either. Stars, we can, that's reasonably reliable because, for instance, we can use parallax, we can use simple geometry to work out how far Alpha Centauri is. Because as the Earth goes around the sun, we have a very reliable way of saying we can see stars shift in the sky, so we can get that distance. For more distant stars, we have to use what we understand about stellar evolution. We understand how stars change, and star brightnesses can change in certain ways for certain stars that allow us to get the distance to, for instance, other stars in the Milky Way. When it comes to galaxies, we have to have some other yardstick, and that tends to be supernova, which explode with a certain brightness, and if we measure that brightness, that gives us a guide to the distance. But all of these things are secondary measurements. They're all proxies, because we cannot hold up a ruler and get an actual distance. Most distances on the largest scales have to be calculated rather than measured directly.
I'm going to cut your other questions off there, Sam and Chris, so that Steve can move on to the next topic.
Okay, happy to do that. Right, the next thing that I wanted to talk about is briefly looking at the idea of matter. Black holes suck, and dark matter is a very bad name for dark matter. There's plenty of misconceptions about black holes. That's not altogether surprising because they're such unusual things. You might think of a black hole as being a funnel down which all matter gets sucked. And that's reinforced by the latest images from the Event Horizon Telescope of the black hole in another galaxy or the black hole in our galaxy. But the biggest misconception is the fact that if you generate a black hole, it will suck everything into it, which is just plain wrong, in the sense that if you were to take the sun, which has a particular mass, and if you were to make it a black hole by compressing it, the same mass exists at the same distance from the Earth wouldn't suddenly be pulled into the black hole, because the same mass is pulling on it from the same distance, and therefore the Earth will feel the same gravitational force. So somehow people have got the idea, as soon as you make a black hole, that's it. That's the end of everything, because the black hole will suddenly suck in everything from huge distances. And that's a misunderstanding of how gravity works. In terms of are black holes responsible for all of this weird stuff which we call dark matter, there's a lot of stuff out there which we don't understand. Of all the matter, 16% is the stuff we do understand. That's gas and stars and things. And it's this stuff that is the rather peculiar stuff labeled dark matter. The bottom line is that dark matter is not dark. It's a really bad name for this stuff. So this dark nebula, for instance, is blocking light from more distant stars. So this is absorbing light. Dark matter is only called dark matter because it doesn't emit light, but nor does it absorb light either. So this is not dark matter. This is just dark stuff, dark dust.
So it's called transparent matter.
It should be called transparent matter. It should be called invisible matter, but they were nowhere near as catchy as dark matter, and so dark matter has stuck with us for decades now. We've known about dark matter for the best part of 100 years, but we're still trying to get to grips with it. So if we can't see it and it doesn't emit light or absorb light, how do we know it's there? Well, we can look at galaxies and look at the speed at which stars are going around a galaxy, and we can calculate that stars should move quite slowly in the outer part of a galaxy if there's no dark matter, whereas they should move quite quickly. If you look at the stars on the outer part of the galaxy, the inner stars are moving roughly the same, but the outer stars are moving quite differently. If there was no dark matter, we would expect the outer stars to move slowly. But what we actually observe is that the outer stars of most galaxies move quite quickly, and they can only do that if there's far more mass there than we can account for from simply counting stars. That's why we think dark matter exists. But there's another strand of evidence that tells us there's something weird out there. If we think about the entire observable universe, well, the entire billions of light years of the observable universe, everything used to be a lot closer together and used to be about the size of a golf ball. And over time, over the billions of years since the Big Bang, the gravity that's pulling on all of the matter in the universe is making these small variations in density, the dimples in the golf ball, if you like. It's pulling on those and concentrating the mass into certain structures like these filaments and other voids in between the filaments. And where these filaments intersect with each other, these little white blobs, that's where galaxies are forming. So we can run simulations that tell us how we think the universe came to be in the way it is now. And when we look out into the universe, this is roughly speaking what we see. We see galaxies in structures like filaments, and we see voids in space. But this simulation, we can only get this to work if we include dark matter in the mix. If there's something out there other than the atoms from which you, me, the Earth, the Sun, the Milky Way seem to be made of. There is something out there that is making galaxies rotate at the speed that they do, and there's something out there that has made the universe collapse into the structure that we now see. The embarrassing thing is we have no idea what dark matter actually is. There's a few possibilities, but the jury is still out. Okay, I'll stop there and we'll jump back to chit-chat.
So, yeah, following on from the dark matter thing, I guess the misconception that I encounter a lot is the idea that we don't know anything about it, that it's basically we need a way to explain some things we see, so we just throw in this placeholder called dark matter, and that's it. But obviously, from what you're saying, it's not the case. We have lots of evidence that there is something there. We just currently don't have a knowledge of what it is.
Yes, not only is there evidence, there are multiple strands of evidence. I touched on two of them. One is how galaxies rotate. The other is a completely different way of looking at the universe, and that is, how did it come to be the way it is, based on simulations that try and reproduce the current universe. There's actually at least two other strands of evidence which independently need the existence of something other than stars and gas and dust and all the things that seem to be shining, or at least reflecting light.
And do they
There
agree
are
with each
multiple
other?
strands, but as you quite rightly say, dark matter is simply invented because there is definitely something out there that we are not taking into account. And one way of saying it is to say, well, there's some particles out there that we haven't counted. Maybe there are some black holes out there we haven't counted. Maybe it's actually not the existence of stuff. Maybe it's our misunderstanding of gravity. That's less popular than it used to be. Basically, we don't need dark matter. We need to completely overhaul our understanding of gravity. Most people think that's not the case. Most people think we do understand gravity, and we are missing counting a whole load of stuff. And the stuff might be particles and the stuff might be dead stars, but there's certainly something that is not being accounted for correctly in our spreadsheet of all the matter in the universe.
Yeah, cool. There's been a question from the chat. So if we don't know what dark matter is, how can we do simulations with it?
We don't have to know what dark matter is. The simulations simply have to include more kilograms of stuff. The observations are that stars are moving in such a way that the mass of the Milky Way is more kilograms than we can account for by counting stars. It doesn't actually matter what those kilograms are. Gravity doesn't care if you've got 1 kilogram pulling on 1 kilogram. The gravitational force is the same regardless of whether that kilogram is feathers or lead or neutron stars or black holes or air. If it's a kilogram, it has a particular gravitational force. So you don't have to understand the nature of the matter in order to add this many kilograms into your simulation.
Is there any proof or evidence for dark matter that isn't related to its gravitational effect? Oh, that was a good question.
Let me just think of if it's dark matter lenses, and I'm trying to work out if dark matter which bends space is that. Yes, that's still gravity. So it's the answer is no. Basically, all of the evidence is based on the gravitational effect of mass we cannot account for.
My understanding is that pretty much all of our understanding of space is light and gravity, and so if it can't interact with light, and then gravity is all that's left.
Experiments are being carried out to try and find whether there's a particle that we've missed, and it is possible that we might find evidence of this particle which is not gravitational. In other words, is it possible that dark matter is a particle? If so, is it possible that this dark matter particle might hit an atom and then we see the atom recoil? In other words, that wouldn't be a gravitational response. It would be a different response. It might be an electromagnetic response. But it is possible that we might get evidence that is not gravitational. But so far, the observational evidence that we are using to surmise the existence of dark matter is based on effectively a number of strands of gravitational observations at very different levels. The universe in total, or what's going on in this galaxy, or what's going on in these clusters of galaxies. So we've got evidence at different scales that all point to something is missing.
So yeah, that relates to the question I wanted to ask. So how are we going to find out what this stuff is? So one way is to look for new particles. Is there another?
Yeah, so that's the one that is currently going on, the Large Hadron Collider. People are sifting through the data, saying, are there any interactions going on there that don't seem to fit our standard way of thinking, the so-called standard model? We think we know how particles behave. Are there any interactions? Are there any results? Are there any showers of particles generated that don't seem to fit our understanding of this should happen or that should happen? And if they find something, they hope to find something that might be an indication of, well, only if we had a new particle could we explain why these things interact the way they do. So far, there's no evidence coming out of the Large Hadron Collider that is pointing a smoking gun at anything in particular. And there are other smaller experiments that are doing effectively the same thing, looking for, is it possible that a dark matter particle might interact with something in my laboratory that I would then find gives a measurable detection? Other people are doing other experiments on large or small scales, but there are dozens of different experiments that are all trying different ways of identifying whether dark matter exists as a particle.
Cool. Okay, so it looks like that you our brains are saturated with all this knowledge. We've kind of lapsed into silence, so that seems like a good time to move on to topic number 3.
Topic number 3, misconceptions. Misconceptions over rocket science. After all, come on, it's not rocket science. It can't be that difficult. So the idea of how to overcome gravity, and because of the James Webb Space Telescope, this ridiculous idea of parking at a point in space where there is nothing. This idea of parking at a so-called Lagrange point. So I'm not talking about rocket technology. Rocket technology is awesome, but we're talking here about the science behind it. In other words, effectively orbital mechanics. So orbital mechanics is nothing new. We know, for instance, that Newton got this figured. If you ask a lot of people, what's the purpose of a rocket? Most people will say, well, it's to get off the ground and to go up. Well, no, that's not the purpose of a rocket. The purpose of a rocket is to give you sideways velocity. Newton understood this, so we've known this for 300 years. He had this idea of a cannon on top of a mountain. If you fire a cannonball with insufficient velocity, it will drop to the earth. If you want it to go around the earth, you need to fire it with a very specific velocity. And if you fire it too slow, it'll hit the earth. If you fire it too fast, it'll go somewhere other than a nice circular orbit around the earth. So the idea that a purpose of a rocket is to give you sideways motion is something that's often overlooked by a lot of people. Let's face it, you can orbit at a mile off the ground as long as you avoid mountains and things like that. Okay, air resistance is a problem, but that's nothing to do with orbital mechanics per se. But when you try and explain orbital mechanics, the problem is the maths gets in the way. And people assume that rocket science is complicated because the maths looks complicated. But if you look at the principles are actually quite straightforward. For instance, let's take 2 planets going around the sun. The green planet is closer to the sun, so its gravitational pull is stronger, so the planet moves faster in order to stay in orbit, and you end up with a relatively short year. Whereas the red planet is further from the sun, the gravitational pull from the sun is weaker, so the planet moves more slowly, and as a consequence has a longer year. In other words, the length of time it takes to go around the sun is longer. So
sorry, is that faster and slower in terms of like miles per hour, in terms of like
both? Okay. Yep, it's the inner planet goes faster in terms of miles an hour, as you can see from how far the green object moves, but also it's got a shorter distance to travel, and so both of those add together to give you a much shorter year. But that's all there is to orbital mechanics. That's it. If you're closer to the sun, you go faster to stay in orbit. If you're further from the sun, you go slower to stay in orbit. Everything else about orbital mechanics is just applying the maths. The concepts are actually there. That's all you need. So you can say, right, okay, what about these weird things called Lagrange points? How on earth can you explain those without any maths? Well, let's imagine that green is the Earth and it has a period of 1 year. If an object is, as shown in the red there, it's further from the sun, so its period must be more than 1 year, like, for instance, Mars would be. But what if the red object, what if that orbit was a little bit larger than the Earth's orbit and close enough so that it was pulled towards the sun, and it also got a little bit of a pull towards the Earth as well? There is a particular distance that that red object could be from the Earth, from the green planet here, so that it's at just the right distance, so that the pull from the sun, indicated by the yellow arrow, and the pull from the Earth, indicated by the green arrow, they would add together and give you a stronger pull And that makes the period of this object 1 year. The stronger the pull, remember, the shorter the period. So you might expect it to be 1 year based on its distance, but because of the extra pull from the Earth, it ends up with a period of 1 year. So what does that mean? It means the red object goes round in the same length of time as the green object, because it's getting an extra pull from the Earth, which you notice is always on the same line. It's always in the same direction as the Sun, because they're both going round the Sun in 1 year. So as seen from the Earth, this red object seems to be stuck in the sky. It doesn't seem to be moving at all, because they're both going round together. And that's exactly what the L2 point is. The L2 point is a point such that if you stick a spacecraft there, the pull of the Sun and the pull of the Earth combine together to mean that L2 goes round the Sun in 1 year and effectively follows the Earth. So as seen from the Earth, L2 is a parking spot. Now, one thing to bear in mind is I haven't gone through the maths, and this is quite definitely not to scale, because the distance from the Earth to the Sun is is defined as 1 astronomical unit, and the distance from the Earth to L2 is 100 times smaller. It's only 0.01 astronomical units, so quite definitely not to scale. But the point is, for any system, you can do the maths and you can find a point where the combined pull of the Sun and the object that you're trying to orbit are such that you orbit with that object. And in the case of the Earth goes around the Sun in 1 year, and L2 goes around the Sun in 1 year. So that's a great place to park a spacecraft. Now, if you do the maths, you can obviously get much more complicated. And this is an indication of how we might think about these orbits, because the idea of parking at a Lagrange point can be visualized by this idea of this particular donut. If you imagine these contours are contours of height, and imagine what would happen to a ball wanting to roll downhill, we can get an idea of how you can park at L2. Let's just blow that region up between Earth and L2 and see what's going on. If you look at those contours relative to the red dot that's L2, downhill points towards the L2 point, if we think of above and below in this particular representation, but downhill points away from L2 if you look in the other two directions. So as seen in this sort of contour, we can see that L2 is not on the top of a hill. L2 is not at the bottom of a well. L2 is actually at a saddle point, because the downhill directions are different depending on which way we go. In other words, it's a saddle point, or if you prefer, a Pringle. So the take-home message here is L2 is a Pringle.
Space
and
Pringle.
if you park yourself at L2, if you send a spacecraft like JWST, the James Webb, to the L2 point, because of these arrows at the top of the bottom pointing towards L2, if you drift away in this picture up or down, you get pulled back to L2, so you can orbit. But if you drift towards the Earth, in other words, in this picture, if you move off towards the left, you're going downhill, and you will continue to go downhill until you fire a little bit of your thrusters, use a little bit of your fuel to keep James Webb in position. So you can park at L2, but if you slowly drift off L2, you need a little bit of a nudge just to push you back. And that's why the James Webb, hopefully, will spend many decades at L2, because it will be very frugal with its use of fuel, because it will only need a station-keeping nudge, perhaps every few months, to keep it at what would otherwise be a parking spot. So there's nothing at L2 to keep it there. It's purely a result of that's where the pull of the Earth and the pull of the Sun keep James Webb moving around the Sun with a period of 1 year to match that of the Earth.
Are any of the Lagrange points
back into the chat again? Yes.
Are any of the Lagrange points sinks rather than saddle points?
None of them are gravitational wells.
Okay, well,
there's a saddle point. There's a number of saddle points, but there are 2 points where you might expect things to continually drift away. They're actually hills rather than wells. They're called the L2 and the L5 points. And this is where asteroids tend to collect in the orbit of Jupiter. And you can say, well, how can you possibly have things collecting at L4 and L5? If it was a well and moving away brought you back to the bottom of the well, you might say that's fine. But how can that possibly be the case that if you're on the top of a hill, surely when you start to move off the top of a hill, you're just going to continue rolling down. So how can asteroids start collecting at these 2 points? Confusing. And the main misconception is that we often think about L1, L2, L3, L4, L5, and we tend to think of them as static, but they're not static in the sense that they are rotating around with the Earth. The Lagrange points are points where you can park something in principle and they will rotate with the Earth. We're not talking about a static situation where the Earth is just sitting at a point and we're parking an asteroid or a spacecraft at a particular point. What happens is the asteroid will drift away from L4 or L5, but it will drift away in such a way such that as it tries to go around the sun, it will find that it ends up, as it were, back where it started from. It's a peculiarity of the dynamics of rotating bodies, of systems that are in the process of rotating. And when you look at a static picture of here's the sun, here's the Earth, here are the Lagrange points, you forget that it only makes sense if you remember that the whole thing is turning like a cartwheel. And then you can start to make sense of it. And at that point, it does help to have the maths to tell you what's actually going on.
Because L4 and L5 are the chasing, following points.
That's right. Sorry, I should have said that. Yes, they're the points. For instance, in Jupiter, they're on the orbit of Jupiter, 60 degrees behind or 60 degrees ahead of Jupiter. That's where the Trojan asteroids are collecting. In principle, the Earth also has an L4 and L5 point, but the gravitational pull of the Earth is not strong enough to produce a whole load of big objects there. There's just a little bit of dust collecting at those particular points.
Cool.
Fair enough.
Yeah, I'm not sure I have any questions about that. I wouldn't know what to ask.
Yeah, this is why I wrote the talk on It's Not Rocket Science, because so many people believe that they have no hope of understanding rocket science because it's too complicated. It is complicated, but only if you get stuck into the maths. If you stick to the concepts of what's actually going on, and remember that some people say, you can understand the Lagrange points if you think about Coriolis forces and centrifugal force. Coriolis forces don't exist. Centrifugal force doesn't exist. There is only gravity out there. We invent these other things like centrifugal force, and we invent things like Coriolis force to make the maths easier. They don't actually exist in terms of things that pull on other things. The only source of things pulling is gravity of the Earth and gravity of the Sun, or gravity of Jupiter. And I think people are often confused by people who invent forces that are supposed to make life easier, but for many people, it just makes life more confusing. And that's a question of either how you explain it or how you go through the maths, which of course is two rather different things.
We've got another question from Sheldon in the chat. For the orbits around the Lagrange points, is there a specific size for them for some level of optimal? What sort of size must the James Webb Space Telescope have? I think I'm understanding that.
Yeah, in principle, you could have quite a small orbit around L2. Well, in principle, you can sit at L2 if you wanted to, but that's not ideal for a number of reasons. In the case of L2, it's not ideal because it will be in the Earth's shadow. So your solar panels won't work very well. And so it's easier to make a little bit of an orbit around L2 to stay out of the Earth's shadow. It also makes it easier to communicate with Earth, because if you're on an absolute line, Sun, Earth, L2, then when you're trying to receive a radio signal from Earth, you've got the Sun sitting right behind it, which is a radio source. So you'd ideally be a little bit off to one side. In the case of the James Webb, it's on an orbit which is of order, I can't remember the numbers, let's say 1 million miles. It's big. It's big even compared to the orbit of the moon, for instance. and that puts you a long way from the direct line. You can't have an orbit which is, let's say, 100 million miles, because that would no longer always being pulled by the Earth and the Sun in the same direction. So yes, there is a maximum size. You can't be at a distance that's comparable to the size of the orbit of the planet. You could, in principle, have a small size, but there are practical reasons why you don't want to make it too small. So Gaia is also at L2, the James Webb is at L2, but in practice, it's many hundreds of thousands of kilometers away from L2, orbiting very slowly. It takes many, many months to do an orbit.
Cool. That actually explains a misconception I've always had, because when people talk about these points, you have it in your head that it's, you know, there's this area this big and we're cramming all these satellites in it. But obviously, if they're orbiting the area, you can have a much larger number.
So at its largest point, the orbit is 850,000 kilometers.
Yeah, that's 850,000 kilometers. Yeah, okay.
Is there a specific way they have to orbit? Do they have to orbit like that, or can they also orbit that way as well? Or, you know, obviously satellites.
If that is the line from the Earth to the Sun to the Earth, they have to orbit that way. They have to orbit in the way indicated in the previous diagram, because that's the only way that the object that's orbiting will always be pulled back to L2. If it gets too close to Earth, it'll be pulled to Earth.
Yes, of
course. If it gets too far away from Earth, it'll disappear. So it has to keep roughly the same distance from Earth. That's why it's called a halo orbit, because it's not in the plane of everything else going around the Sun. It's perpendicular to that in a halo around L2.
Awesome. Okay, well, that brings us on to the last topic.
And easiest.
I can't remember what it is. I'm quite excited.
Quantum mechanics. So we're moving away from the large-scale structure of the universe and how we get rockets to different planets. This is going inward and asking ourselves about what things look like on a small scale. So we might have this sort of picture of what we are made of. I'm sure everybody knows we're made of atoms. That's no surprise. But in terms of, well, how do we depict atoms? How do we describe atoms? How do we model atoms? This is a quite common picture of what we think an atom might look like. It's not a particularly good one, because it doesn't tell us that actually if this was an atom with, 5 electrons in it, those electrons should have different energies. And so this might be a better picture for a multi-electron atom. Who knows which one this actually is? I haven't counted them all. But the idea is that the electrons are at different distances from the nucleus and hence have different energies. And that's a little more realistic than assuming all the electrons are at the same distance. But notice that although it has some similarities with the solar system, it's quite different in the sense that, for instance, we can have multiple electrons in what appears to be the same orbit, which doesn't usually happen in the solar system. It doesn't happen for planets, but as we've just said, it is possible for instance, asteroids to share an orbit with a large planet like Jupiter. So this is perhaps a better way of thinking of electrons in an atom. And the top picture is very good as a two-dimensional representation if we want to draw it on a piece of paper. But we must remember that atoms are actually three-dimensional. So we really ought to think of them in shells rather than in orbits or in rings around the nucleus. But one of the big problems with this particular way of thinking about atoms is it does imply that an atom is clockwork, that it's got a nucleus and it's got these electrons buzzing around like the Mercury or Venus or Earth going around the sun. And that is the real problem with that way of thinking about atoms, because atoms are not based on clockwork. A better way of thinking of them is that the atoms are based on the probability of electrons doing certain things in atoms. If we think about the Earth going around the sun, it's always, roughly speaking, 150 million kilometers away. It's never half that. It's never double that. The Earth-Sun distance is not quite circular, so there is a little bit of ellipticity there. But roughly speaking, the distance from the Earth to the Sun is always about 150 million kilometers. But for any given electron in an atom, it might spend some of its time close to the nucleus and some of its time a long way from the nucleus. And these little graphics here are supposed to illustrate the fact that the probability of finding an electron at any particular place is based on a mathematical principle which could put the electron arguably anywhere in the atom, or indeed anywhere in the universe, you could argue. So we have this problem. How then are we going to describe atoms if they are not clockwork things like little mini solar systems? Well, we could describe atoms in terms of words, and we can talk about particles like electrons and protons and neutrons, or we can talk about the spin of an electron and an electron orbiting a nucleus, and we can talk about energy levels. But unfortunately, all of those words come with baggage, because when we describe atoms using these words, we don't mean quite the same thing as we do when we're talking about the spin of the Earth and the Earth orbiting the sun. We're using words to mean different things when we're talking about atoms compared to, for instance, the solar system. So instead of words, should we use pictures? But I've just said the pictures can be misleading. We shouldn't think of a clockwork picture, and even clouds of probability aren't necessarily the best way of picturing what an atom actually looks like. So if words don't work well and pictures don't work well, what are we left with? Yeah, sharp intake of breath. The only thing that actually works with atoms is maths, and the maths seems to work. We don't necessarily understand why, but maths does seem to describe how atoms behave. But of course, if we want to teach maths to a student, we have to use words to describe what we're talking about, and it helps to use pictures to try and explain what we're dealing with. But the real misconception behind all of quantum mechanics is because quantum mechanics doesn't agree with common sense, it is so difficult to give up on common sense. And it's so difficult to say, well, if quantum mechanics describes something that disagrees with common sense, you have to throw common sense away and you have to trust the maths. And if you don't trust the maths, you can't make any headway. Even the architects of quantum mechanics had a problem with this. How are you supposed to describe atoms by using a language like this? You might get away with it when talking to an undergraduate physics student, but apart from that, how are you ever expected to talk about what atoms actually are? Werner Heisenberg, one of the architects of quantum mechanics, said, "We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. English, or indeed any natural language, is not sufficient to talk about atoms. Language was developed to talk about common, everyday, common sense things. Language was not designed to talk about atoms any more than it was designed to talk about an expanding universe." The other architect of quantum mechanics was Erwin Schrödinger. Atomic physics has shown us that atoms have no meaning, but can only be understood in experimental measurement. That's a hell of an expression to use. We don't really know what atoms are. All we can say is that if we have this mathematical structure called quantum mechanics, a whole set of mathematics that describes how atoms and molecules and other objects are supposed to behave, the maths tells us what we would expect if we make a measurement of what light is going to come out of this atom, for instance. Quantum mechanics gives us the answers, but Schrödinger here is saying the maths is right, but the concepts that we're building have no reality as such. The really weird thing is that we can use quantum mechanics to build ourselves a microscope, and here we're seeing a microscope image, and notice the scale is less than 1 nanometer on each side, 850 picometers. So on this scale, we seem to be seeing atoms, and yet atoms have no reality. Atoms are described by mathematics, and yet we can build microscopes that give us these little blobs. Are we fooling ourselves into thinking that these are real objects? Bear in mind that if we are looking at a material, this happens to be carbon, on this scale, a grain of sand would be about the size of the moon. And whenever I see an image like this, I always think of William Blake, to see a world in a grain of sand. So, do atoms exist? Well, let's think about discussing. That's the end of my 4 sections. So let's go back to the discussion points.
Wow. Do atoms exist? No big questions here. Wow.
That's quite a small question, actually.
Yeah. Yes. Fair.
And you could argue it's philosophical. Are they
Yes.
simply a mathematical construct that help us understand the real world? Is this thing actually solid, or do I just think it's solid? If this is solid, how come atoms are so nebulous and ghostly, and yet when atoms apparently come together, they give us something which is quite definitely solid? But solid is a concept that doesn't exist at the atomic level. Where does that concept come from? How many atoms do we need to put together before we get common sense back again?
Is solidity like an emergent property of
Yes,
atoms,
that's
then?
precisely the point. And we can't necessarily define at what point it emerges. So there are various quantum mechanical predictions that say an atom should do this, an atom should do that. If we ask, where is the electron in a hydrogen atom? The answer is it could be anywhere. There's a certain probability it's quite close to the nucleus. There's a smaller probability it's a long way from the nucleus. There's a tiny probability it's in Alpha Centauri. There's a really small probability that it's in the Andromeda galaxy. But in principle, we cannot say an atom is this size. We can only talk about the probability that an electron exists at a particular point in space, at a particular point in time. There is no concrete reality to that. But if atoms make molecules, do we say the same thing about molecules? If molecules make a cat, do we say the same thing about a cat? Is a cat real?
Definitely in a basket, right?
Well, okay, you say that. I don't see a cat there, but okay. So it's this problem of when does the macroscopic world transition to the microscopic world? We have theory that tells us how the microscopic world works, and we think we understand how the macroscopic world works. But there is no dividing line. Where's the grey area between the two?
I was going to ask, is there a particular scale at which you go, okay, right, forget your quantum mechanics, we're now on regular mechanics, or vice versa? Like, here's the border check.
No, you can't define an absolute boundary, and it depends on what it is you're trying to measure. So you can build yourself a quantum computer, or you can build yourself a microscope, which is a macroscopic object, but it works according to quantum mechanical principles. A scanning tunneling microscope. I didn't mention that at the time, but that's how a scanning tunneling microscope works. It works on the principle of quantum tunneling, which is an essentially quantum mechanical phenomena. It should not work according to classical mechanics. That microscope should not produce images, but it does, telling us that quantum mechanics does work. And we can build a microscope that it exploits that, and maybe we'll build quantum computers that exploit that. If you're familiar with the idea that on the microscopic, on the nanoscale scale of things interfere with each other, in the sense that if an electron goes through a slit, it can interfere with another electron or itself going through a different slit. How large an object can you send through 2 slits and end up with wave-like properties? It works for an electron.
Interfere with itself going through a different slit.
Yes. The electron goes through both slits at the same time. I never said that this makes any sense. I said explicitly it goes against common sense.
You explicitly said it doesn't make sense.
Yes.
Common sense.
And the only way to make sense of quantum mechanics when you send electrons through a slit is to say, well, it must go through both slits at the same time. And if you try and measure which slit it goes through, the experiment changes. So in other words, nature can't be fooled. No matter how careful you try and do it, nature can't be fooled. But the question is, how big an object can you send through 2 slits at the same time? Can you send an electron? Yes. Can you send a small molecule? Yes. Can you send a large molecule? Yes. It's been done with a virus. A virus has been sent through a double slit experiment, and it's been proved that the virus goes through both slits at the same time.
That's crazy.
Now, no one has yet tried it with a cat. So somewhere in between viruses and cats, something must change. Or we just have to figure out how to do the experiment with a cat. In much like the
Well,
thought
that's something to do
experiment
at
of
the weekend.
Schrodinger's a cat, we need the equivalent of Schrodinger's cat sent through a slit experiment.
Just,
You have to throw common sense away.
Yeah. I think the
yes,
take-home
so
message of this evening is that, you know, we can do lots of things with this knowledge, but we don't actually understand it.
A lot of people are spending their entire lives trying to interpret quantum mechanics. Some scientists say, don't bother. Some scientists say, shut up and calculate. Quantum mechanics works. Put this number into this equation, you'll get the right answer. Quantum mechanics has not yet, after 100 years, produced the wrong answer. It's never produced something that does not agree with what we actually see. So quantum mechanics appears to be correct. And some people say, don't worry about it. Just use it as a really useful calculation tool. Other people worry about the fact that Schrodinger's cat tells you all sorts of weird things. And in a sense, scientists come into two camps. You either worry about it and lose sleep over it, or you don't.
Or you shut up and calculate. My new catchphrase.
Yeah.
So, there was a question from earlier
but
related
kind
to
of-
your first point about
it came up just as we'd left the subject. But so with the expanding space, as we can only measure relative to ourselves, do objects at the same distance away travel at the same rate?
As far as we can tell, yes. There are some people who argue that there are small differences. If we look at that cluster of galaxies over there, it doesn't appear to be receding quite the same as that galaxy cluster over there. But on the whole, it doesn't matter which direction you look. In other words, the universe appears to be isotropic. It's part of the cosmological principle. We do not live in a preferred part of the universe. Therefore, in principle, everything should look the same in all directions and everything should behave the same in all directions. And some people take that as it must be that way. In other words, if you've got a slight measurement difference between these galaxies and those galaxies, it's because you haven't measured it accurately. A lot of people believe that fundamentally it must be the case that all of the universe is the same and there should be no difference to looking left to looking right.
So there's no center to the universe where everything expanded from?
Yes. In other words, it's part of the cosmological principle. Let us assume that we're not in a special place. If you break that and say, maybe we are in a special place, then it's very difficult to make generalizations, because everything you observe, you could say, well, that's because we're in a special place. It only looks that way because we happen to be here. That's why people adhere to the cosmological principle, because ever since we realized the Earth wasn't the center of the solar system and the sun wasn't the center of the Milky Way, we've come to the conclusion we should not place ourselves anywhere special. And that's embedded in a lot of theories, that it must be the case that if you take a large enough scale, the universe must be isotropic. I know it's not isotropic on a small scale, because if you look down, you see the Earth, and if you look up, you don't. So clearly things are different on a small scale, but on a large enough scale. And part of the discussion is, well, how big a scale do you have to go to before that is necessarily true?
Okay. Well, that was fascinating. I think that's a good point to end on. We've reached the time we usually call it a day. Steve, that was mind blowing. I'm going to have to go lay down for a bit after that. It was absolutely fascinating. I think I've learned so much this evening about things that I thought I knew a little bit about, but obviously didn't. I'll introduce what we've got coming up next time. So in a couple of weeks' time, we've got Dr. Faye Skelton coming to talk to us about the making a murderer effect, which is basically about why people confess to crimes they didn't commit, which should be really interesting. Before we sign off, Steve, I'll give you a chance to just say anything else you want to say about yourself. Where can people find more information? I've put the link to your other talks down in the comment bit down there. What they call it, the doobly-doo, I believe, is the technical term for it. But yeah, do you have anything else you want to sort of talk about?
Not in particular, but I've just put another link into the chat, which if you could transfer that to Joe Public, That's the slides of this particular talk. If anybody wanted to go over anything that I've said in the last hour or so, I've already given a link of other talks I've given, but this is just the slides that I just presented today.
Awesome.
I'm more than happy if anybody wants to look at either of those two sets of links and pick up my email, which you can find from various places, or just Google me. I'm very happy to answer questions by email if anybody wants to follow up anything that we've discussed this evening.
Awesome. Well, thank you very much again. And thank you everyone for joining. We have some good questions from the chat this evening. We'll all say goodnight now, and we'll hopefully catch you all in a couple of weeks' time. So good night, everybody.
Good night.